Security is tough. It's really hard to know when you're doing it right because bad security and good security basically look identical. Figuring that kind of stuff out is a whole profession. In fact, it used to be my profession. I come out of this InfoSec world before I came and started being a Cocoa developer. But most of you really don't plan to spend that much time studying cryptography and security systems and risk assessments. Really, I think what you want is to know how to be reasonably secure, right? Secure enough that it won't be embarrassing when things do go wrong, right? So today we're going to cover some basic and fundamental technologies in iOS that are available to help you secure your users' data. And have maybe at the end a small toolkit of things that you can do when you go back that you can implement practically. So all of the notes and everything are all going to be on this GitHub repository. I'll put it up again at the end. You'll have to scribble it down. And for those of you maybe going and looking at it right this minute, I swear I'll have it updated before the end of the day. Not quite. So I'm going to start with the most important thing you can do. The biggest bang for the buck. Encrypt your traffic. If you picked one thing, HTTPS. If you don't do anything else for security, turn on HTTPS. You get a whole lot of things basically for free. And it is a great example of the best practice because even done wrong, even if you kind of mess it up, it tends to be much better than nothing. And that's not true of all security things. Sometimes you can make things worse. For the most part though, HTTPS, just turn it on. Now, the thing is, you don't have to turn it on anymore because Apple is forcing it on us with ATS, right? We get this app transport security. So what you really need to do now is stop turning it off. I know a lot of you are turning it off. Stop it. Now you're going, oh, but I have an advertising partner, and my advertising partner can only distribute me things over HTTP, unauthenticated. So I have no idea who I'm talking to. And also they can't list all the sites they're going to connect me to. It's going to be random sites all over the internet. Say that out loud. And I'm just going to display anything I get to my user without even knowing how to get another partner. I'm dead serious. If that is the best they can do, you have the wrong vendor. So, okay, you turned it on. Great. We could just end the whole talk, right? Let's go just a little bit deeper. So most of the time, that's fine. Most of the time, just turn it on and you're actually pretty good. But you may have an InfoSec team in your organization, and they may have read OWASP. And in OWASP, which is a big security best practices guide, and it says, pin your certificates. And they're going to come to you, and they're going to say, pin your certificates. And you're going to go, what does that mean? And they're going to go, I have no idea. It's in OWASP. So I'm going to tell you now what it means, what it's useful for, and how you would do it. So, what problem are we solving? There are 168 roots in the iOS keychain. There are 168 roots in the iOS keychain. And you expect many of these. VeriSign and network solutions. But there's a number that you really maybe don't expect that you're also trusting anything they give you. One of those, you see the one AOL, Cisco, Apple. I actually helped put the Cisco one in the root keychain. I assure you, you don't need to trust my cert. It's not for you, it's not even for websites. It's bizarre that it's in the keychain. But you trust it, by the way, you trust my cert. It's actually a great cert, it's very well secured. But I don't know who EchoWorks is. I don't know who these people are. Why am I trusting them? You have to protect, when you have a certificate of your own, you have to protect its public key, or its private key, sorry. You have to protect its private key. That's just how it is. You can't get around that. Well, but you're also trusting that whatever roots you trust, you also are trusting that they're protecting their private key. And I promise you, VeriSign does a very good job of protecting their private key, but it is always riskier to trust 2 people than 1 person. Always. So, what can we do about it? How can I reduce the amount of trust I have to do? And the answer is this thing called certificate pinning. It just means I'm going to limit how many certificates I trust. And so instead of 168 roots, I have 1 or 2. I have some small number of roots that I trust, maybe all the way down to just the exact certificate that is on my server. I say, this is the one and only. I only trust it. So, or you go all the way up and say, look, I always get mine from VeriSign. I'm only going to trust certs from VeriSign. All this kind of stuff. So how do you actually do it? The code is kind of tedious. It's about half a page to a page of code. It's not that hard. You can go look it up. But why? I wrapped it up in a thing called Certificate Validator. And for common problems, if it's, the normal things you want to do, you just take your public key that you want to trust, or a list of them, create a certificate validator, and make it the delegate of an oral session. Now, if you want to have a little bit more control over the world, just look at the code. Like I said, it's about half a page of code. You'll understand it. If you need something more complicated, there is some stuff out there called TrustKit. I'll have all these links up later. There's this thing called TrustKit, and TrustKit has a lot more features. I mean, it does all kinds of things. I find it a lot harder to use. That's why I made Certificate Validator, because it's just you drop it in and you're done. If you want even more, because this is really all you really need to know for most purposes, so we're not going to go deep and deep and deep. But we have an entire session for free at the OpsCIO folks, the Swift Talks on certificate pinning, and I'll have that link up later. There is one big problem that comes up all the time in certificates, which is rotation. The problem is certificates expire. So it's always a problem with certificates, but with pinning it becomes a bigger problem because you've just baked some cert into your app. How do you deal with the fact that it's going to expire, right? Then your app's going to stop working. This, by the way, is why you should not use pinning if you don't need it. You should think about, do I really need this? Because you are signing up for some headaches, and you will probably screw up your app eventually if you're not very careful. But going down this road, this is my recommendation. I like to get 5-year certs, and then I pin to the first one. And of course you bake that into your app, right? And you ship it out. And then after 1 year, I go buy another 5-year cert. And I start baking that one into the app. Now there's 2 certs that I trust. But I'm still doing the first cert is the one on the server. After the second year, I switch. And so now my users have had a year to upgrade. My users tend to upgrade very well. If you have users who don't upgrade that fast, maybe you have to spread this out. But your goal is to constantly be having this cert and the next cert are always kind of baked into the app. And that way you don't get burned. Why so fast? Why TikTok year? I say don't go longer than this. Or don't. Make sure you are changing them more often. You might have to have 3 or 4 certs baked into the app because people don't upgrade, but don't wait longer than about a year or 2 at the most. Why? Because everyone will forget how to do it. If you wait 4 years, I assure you, you will wait 6 years and it will fail because everybody will have rotated and nobody will remember that you have to do this. If you do it every year, people will have a hope of remembering not only that I needed to do it, but how to do it. So touch it every year, just to keep it in your heads. And that's it really, encrypt your traffic. HTTPS, pin your certs, rotate them right here. Data protection. Okay, so you downloaded all this sensitive data, and how do you keep it safe on the device? So iOS provides built-in data encryption, and for the most part, you should be using it. Whoa, that's backwards. First, okay, there are 2 kinds of encryption on iOS. One is called device encryption. That one ties flash storage to a CPU. We're not going to talk about it because you have no control over it. There's nothing you can do. This is actually the one that if you remember the whole big story with the FBI trying to get into the phone, that's the one they're talking about. It's irrelevant to this conversation because you can't turn it off, you can't turn it on, doesn't matter. What we're going to talk about is called data protection. It's a file level protection. And you do control that. Now, I'm going to explain how it works. I'm lying to you. It is way more complicated than I'm going to say. But you don't need to know all the ins and outs. I will give a link a little later of Apple's full gory details on key bags and elliptic curve. And there's all kinds of stuff going on that is more complicated than I'm saying. But this will give you the flavor of how it works practically. And this is how I keep it in my head so that I write my apps correctly. Okay. So I've got this document, And I mark it, I want to protect it, so I mark it, and we'll talk about how to mark it in a second. I mark it, file protection complete. The important word there is complete. And the system will then derive a key, a special key, using the user's PIN. And yes, this only really works if the users have PINs, or if they have passwords, if they somehow lock their device. If they don't lock their device, it's a problem. Anyway, it generates that key, and it immediately encrypts the file. But the key is still in memory, so you can still keep using it, and it's completely transparent to you. You don't realize you're talking to an encrypted file. All transparent. Now, when the user locks their device, within a very few seconds, it shreds that key. In fact, that key lives in a part of memory that is designed to be destroyed. It's harder than you think to get things out of memory. And now it can't be accessed. And that means it's instant. So it doesn't run over and encrypt it when you lock the device. It just stops decrypting it. Then the user logs in, they enter their PIN, they use the PIN to generate a new key, and now you can access it again. The trouble is, that's great, but like I said, pretty much the moment, it's within a few seconds. When the user locks their device, you lose access to all your files. In many cases, that's actually fine. But there are quite a few files that sometimes is a problem for. Maybe you're downloading a file, or you have a log, or you need to do something. So sometimes you need a little less security so that you can clean up. And so that you can keep doing things in the background. Or maybe you actually do things in the background. You have app refresh, or you have whatever. How do you do it? So the main protection level is called complete. That's what we were just talking about. It says, always, whenever it's locked, we're gone. Then there's complete unless open. That says, if when we locked, I had the file open, leave it alone until I close the file. You can also add that flag to files you create that counts as opening. So you can actually create new files in the background. If you create them with complete when you're in the background, you then can't write to them. So you have to use unless open. And then there is this very low level called complete until first user authentication. This only protects it for a very short window. It's between the time the device is booted and the very first time the user unlocks it. And then it never is encrypted again until you reboot the device again. Now this sounds useless, but it actually is useful for a lot of cases. Not as good as you'd like, but a lot of attacks to jailbreak, for instance, require rebooting. It's not always true anymore, but a lot of things require rebooting. Well, that encrypts everything for you. So, better than nothing. How easy is it to do? Just turn it on. Actually, this used to be really hard. You had to do all this stuff, but now you go next code and just flip the switch. Switch, you say, yay. That turns on for complete. It changes your cert, it puts it in the entitlements, it creates all the stuff you need. How do you do it in code? Okay, so that just set it kind of by default, but you need to be able to set these permissions. Sometimes you need to set the permissions up or down. And you don't have to turn that, you do have to turn that on if you want to do it at all. You can change the default by going, if you go to the App Store website, if you go to the website, you can change what the default is, but you can't do it in Xcode. When you want to set the things, you can, all the various pieces, data, string, array, all the things that have a write method, they all take options. And one of the options you can pass is the protection level. So that's one way to do it. The way that's much more common, this is great if you use those, it's just those don't come up that often. This is nice because though it's encrypted from the moment you start writing. This comes up more often. And don't bother scribbling it down. Once you kind of have in your head that file manager can do it, it's not that hard to look up what the actual attribute is, but there's an attribute that file manager can set called file protection type that goes on the protection key. And once you can turn that on, it changes the permission level. This can be done at any time. This can be done on any thread. This can be done while you have the file open. This is pretty fast and pretty much completely transparent. So don't be afraid to make this call, even while you're in the middle of writing the file. It's really common to call this, like during startup, you might go through and fix the encryption on all the files in the documents directory. You just loop through them all and set their permissions. And sometimes it's common, like when you're going into the background and you know you have some stuff you have to save, or you have to work on, you can call this right on the way out. Again, it's very fast. And you can do this to anything. It does not matter. Core data files, SQLite, images, it doesn't matter. Works for everything. You also, of course, can find out, hey, is my data available? This is really, really useful when you wake up in the background. During app refresh, true story, we would wake up and then it's like we couldn't find anything. It's like nothing worked. This especially also works with keychain when keychain has the same levels of protection, and so sometimes you'll wake up in the background and you suddenly can't talk to keychain and you freak out. It's kind of nice to be able to say, hey, is protected data available? You can ask before you go messing around. On UI application, there's a bunch of delegate methods and notifications. Again, once you kind of know it exists out there, it's pretty straightforward. As I said, this is the full gory details. This document fascinates me because Apple really does dive into a lot of the details of how they do it. You'll notice the word business in the middle, and that's a lot of why it exists. Now, good security should be out in the open. You should be able to tell people everything about your security, exactly how you implement it. And the only secret in the whole system should be the secret. That's how you know it's security and not just obfuscation. And when I was in InfoSec, it was important. We said, in places like this, we said, look, Apple, we're not going to let our users use your devices if you won't tell us how you're protecting stuff. And so they make that stuff available. It's a really complicated document, though. It's fun to read if you just would like a little bit of peek behind the curtains of cryptography. So, data protection. Turn it on! Turn it on. Actually, one thing I do want to make a point of, turn it on early in your project. You will create bugs with this. You will screw yourself up at least once where you don't have access when you meant to have access. So don't go flipping this switch a week before you ship. Because you will, I promise you will have an annoying bug out of it. But it's still worth doing. Turn it on. Turn it on to complete and set things different ways using the file manager, mostly. Passwords. Seems every time you turn around, there's a new password leak. It's crazy. I want to be clear that no matter how trivial the information that you have in your app, you have this cat fanciers, cat video collection app, and people can log in and leave comments. So who cares? Who cares if somebody hacks your password database? People reuse their passwords all the time. So I promise you the passwords in your database are also the passwords for their bank account. You must consider every password, username and password, to be precious and to be sensitive, no matter what it's guarding. So how do we fix it? How do we deal with it? The best way to protect passwords is not get them. You would like to never see them. You don't want to see them at your server. Well, how can we help that? How can we fix that? The simplest, and this isn't enough, but we're going to start with this, is just hashing, right? Don't send passwords, just send the hashes of passwords. And the hash, the whole point of a hash is that I can't go back the other direction. So anytime I'm talking about hashing here, I'm talking about cryptographic hashes. Cryptographic hashes are nothing like the hashes that are like string.hash. You can't use that. That's a completely different kind of hash. It's meant to be fast. Cryptographic hashes have a number of important properties. The most important being it's very, very, very hard to come up with collisions, and it's very, very, very hard to move them backwards. So the idea is that given that I know that string, there's what we call, there is no computationally efficient mechanism, which means I can't do it without just guessing everything, of getting backwards. So, I sometimes tell folks, it's like, look, I know you have this server and it can't handle any of the things I'm about to tell you. And you're not allowed to touch the server and you can't change anything. Just hash your passwords and treat that as the password. It's not good enough, we're going to get better, but that's actually, you get a lot of benefits of now you never have to see it, and you hashed it into some string, a hex string or a base64 or whatever you want, and now the whole system just uses it, right? It's still a string, it's just a different string. Okay, why do I keep saying, but that's not good enough? Actually, I want to talk about a different thing first. I want to talk about choosing your hash. I used to have a big complicated slide here where I walked you through which hash should you use for what purposes and when do you need to, no, there's only one answer, use SHA-2, period. There are no other answers. SHA-1, well, MD5 has been broken for years and MD5 can be reversed in minutes now. I mean, it's great, seconds actually, you can create collisions in MD5, it's crazy. SHA-1 has recently been kind of cracked. We can have a big discussion later about what that means and how important it is and whether it can be used. It doesn't matter. Once things have been kind of cracked a little bit, they crack a lot really fast. That's how it works in crypto. SHA-2 is looking very strong. We like SHA-2. It's a nice algorithm. There is a thing called SHA-3. There are hardly any implementations of it. Don't worry about it. Eventually SHA-2 will fall. Something will happen and you'll go to SHA-3, but don't worry about it. Use SHA-2. Oh, if it were only that easy. The thing is, you'll never see the word SHA-2, you see these. Luckily, security people always make things easy to understand because they put SHA-2 right in the names. Dang it, they don't. So all of these are SHA-2. Like you can tell, SHA-512, that's clearly 2, right? Yeah. Most of these you don't care about them. Most of these you don't care about at all unless you're working on really, really ancient systems that can only talk like triple des. On an iPhone, really? You're never going to need any of these. You're going to need 2 of them. Or most of these. You're going to need 2 of them. You're going to need 256 or 512. And for practical purposes, the only difference you really need to worry about is 512 is 64 bytes long, and 256 is 32 bytes long. If 64 bytes is not a big deal for you in your record space, use that. It's more secure. If that's enormous, and 64 bytes is a lot of bytes, and 32 bytes would make things awful easier, use 256. 256 is plenty strong enough. It's for most, there are places it's not strong enough, but it is very, very strong for almost all the purposes we'd be talking about. It's just 512 is stronger. Pick your poison. So, what happened? I don't know if people remember the big LinkedIn password loss or whatever, when we lost all the stuff at LinkedIn. But basically, attackers broke into LinkedIn's database, stole everything, and they started cracking people's passwords, left and right? And using it, like I said, they took the logins from LinkedIn and went in and started using them in bank accounts. That's exactly what they did. But the thing is, LinkedIn actually did hash their passwords, just like I told you to, right? They used SHA-1, but that wasn't the problem. Nobody cracked SHA-1. It wasn't because they cracked SHA-1. They did it. They hashed the passwords. Yay on them. Except it didn't work. It wasn't good enough. So I told you, okay, here's a SHA-1 hash, and I told you there is no computationally efficient way. There's no practical way to turn this back into a password, right? I can't go that direction. It's called trapdoor function. You can go one way and you really can't go the other way. But I can do a different thing. I can just guess passwords, because people are really bad at them. And there aren't that many, frankly. In cryptographic terms, there's a tiny number of passwords that exist that anyone uses. And so I can just start guessing them, and then I hash them. And I create a giant database, and this thing, I can't remember one that I can guess you can get databases now. They're called rainbow tables. You can get one that has every possible password up to 8 characters long, lowercase, if it's lowercase and numbers. And I can't remember, it's in the hundreds of gigs. It's not that big a database, right? People use that kind of stuff, and there are much bigger rainbow tables out there that use it and that don't have to deal with every possible password. They can say, well, the common ones, all the hashes are out there. Okay, so what do? I just guess and guess and guess and guess and guess, and then I go, oh wait, look, I do a database lookup, and I go, that's the password that generates that. So, using this, I probably am not going to be able to get any particular person's. I can't pick somebody and go, I'm going to find out their password. But what I do is I steal millions of passwords, and I'll break a lot of them. And once I have broken somebody, I know every other person has the same password. And people use the same passwords a lot, even when they think they're being clever. And if you're swearing in your passwords, I assure you, you're using a common one. Everybody swears in their passwords. I don't understand that. Salting. So how we fix it? First thing we do is we call salt. To salt something is to add a little bit of data, of random data. And so like I said, I have this secret password, and it turns into that hash, and on this other site, I use the same password. Well, what happens if I just add a little prefix? In one, I did XXX:, and it creates a completely different hash. And why would I colon? A completely different hash. And one of the important things about cryptographic hashes is you should think of these as random strings. There is no useful relationship between them, even though they're very similar. Strings, they have very, very, very different hashes. Okay, so that's good. So I need a salt, though. What's the salt going to be? Well, the point is that they be different for every single password you have. Every single one on your machine should be different, and it should be different than anybody else who decided to do the same thing. The best thing you can do is random. You just pick 8 random bytes. That's awesome, right? Because you're not gonna collide on 8 random bytes. But it's a pain, because the way you'd have to log in is you then have to say, I take the username, I connect to the server, I ask for what the salt was that was used, and then they send it back, and then it's not worth it most of the time. Not for passwords, usually. Instead, what I always recommend is a deterministic salt. This means that I just have a rule for creating the salt that makes sure it's unique. What I like is I have some prefix that identifies my database. Reverse DNS is great, your app bundle ID, these things are great, right? Because nobody else is going to have that same string. A colon, and then, or not a colon, whatever you want, and then like the user ID, because again, that's unique for everybody. So that's great. Now it's unique. Every person on my site is going to have a different salt, and they'll have a different salt even if somebody elsewhere uses the same idea. Does it exactly the same way. It's important, salts are not secrets. Salts, do not assume people don't know what your rule is, right? They can totally know what your rule is. Not a secret, it's just stopping them from building rainbow tables. The thing is, there just aren't that many passwords. So while this will help stop people, this will stop them just like, blah, I'm gonna find 60% of the passwords in your database, they can still just start at the first one and start guessing passwords. And they just guess them really, really, really fast. Until they, and try to cycle through the whole list. So what do? Well, we fix that by making things slow. How do I make it slow? That's called stretching. Because real passwords are really easy to guess. And we want to make guessing expensive. So if I could just add an extra 80 milliseconds, which is a target that I often have, of like how much time I want to take. You can't notice 80 milliseconds or 100 milliseconds, right? As part of your login. Less than 1/10 of a second, right? Extra time. Nobody's going to notice it. But I go from a couple of months to crack a password to 15 million years. In crypto, we love things that have like billion, million, we like big numbers, right? So no matter how much, so that when you make your computers 10 times faster, 100 times faster, 1,000 times faster, maybe I can get this into 1,000 years, right? That's why I want lots and lots and lots of, I want my numbers to be enormous, because when attackers make things faster, they don't make it twice as fast. They make it 4,000 times faster, right? 1,000,000 times faster. You need lots of headroom. So how we get that headroom? We use a system of stretching, and you should use a thing, there are a number of options, but the one you should always use is PBKDF2. It's very ubiquitous. We'll explain later why it's called that, why it's called PBKDF2, because we'll see it elsewhere. But all it is an algorithm that's built to be slow and be really hard to do in parallel, so that you can't just like fork it out to lots of GPUs or something. This is an example of how you use it. It's very ubiquitous on lots of platforms. This is using CryptoSwift. It's a decent library. I like CryptoSwift, but it is a low-level crypto library, which means it gives you no safety rails. It assumes you know what you're doing. In this case, though, it just needs a salt and some number of iterations. I said because what we're going to do is we're going to do this thing. We're going to do this SHA-256 hash. You see, variant.SHA-256. We're going to do this hash. We're not just going to SHA-256 a bunch of times. That actually is shortcut. There are tricks to shortcut that and make that fast. There's a little tricks that they use to make it so I can't. But one of the pieces is going to be a hash function. And one of the things you need to know is how many times to do it. All of the things in your system need to agree on this. They can be anything though. I like numbers. I like that iterations number to be like 10,000, 100,000. These are the good kind of numbers. Variant, I like SHA-256 here. Anything's fine. Doesn't matter. And actually, you'll hear, yeah, keep going. It's okay. It doesn't matter. Remember, this is not really about security. This is about making things slow. You can use anything there. It is totally secure to use MD5 in PBKDF2. It doesn't matter. Because you're not using the hash function for security. You just need something, the security proof on this requires a very low bar of how good that hash function has to be. It can be a really bad hash function. I mean, it can't be string hash function, but any crypto hash will be plenty. But use 256, SHA-256. Okay, you've done this thousands of times. I want you to do one more hash. They're going to then, so they on their side, they do all this hashing, all this PBKDF2, stretching, everything. Then they send it to the server, and they're going to log in. And you have a thing, and you have something in your database, and you're going to compare them, right? I want you to SHA-256 or whatever, do one more SHA hash on the thing you get, and then compare that to the database. So what? Why? I mean, I just did it 10,000 times. Why 10,001? The point is, the 10,000 times was to make things slow before it got to you. So you actually don't know their password, right? It happened on the local device. So you never see it. Great. That one more is to make sure that if I steal your database, I still can't use the things I find in it to log in. Right? If I just took the thing that the user sent me, it's basically now a password. I mean, if I just stick that directly in the database, I mean, it's not a risky password. It can't be used anywhere else. But if I steal your database, I can pull the usernames and this hash and log in. I don't want you to do that. Because then I don't realize that, because I don't tell you I stole your database, right? I mean, I just start logging in. But if I do one more hash, now I take this random noise and I create a different kind of random noise that, again, I tell you can't go backwards. So they're not going to be able to use that stuff. Once you do that, you could take your database and stick it on the internet. Please don't do that. But you could. Okay. So that's going to end on passwords. Hash, salt, stretch. Hash one more time. Let's talk about AES. Everybody talks about AES. Everybody likes encryption. Not every, but pretty near every system that I see that uses AES does it wrong. This actually got me into building libraries and the like, because I kept going to people, you're doing it wrong. Everybody goes, oh, AES encryption is so very powerful. So very powerful. It cannot be, the government. Yes, it is. It is very powerful. It is very powerful. But if you use it wrong, it is not. You have a super strong lock, and you leave the key in it. It does not matter how strong the lock is. And if you use AES incorrectly, you have the same problem. So we're going to talk about how to do it right. First, I'm going to tell you, I'm going to skip to the end. What's the end point? The end point is using my library. I hate to show this. I hate that I had to write this, and I really have to look for years. I've been maintaining this thing for years and years. And I've been trying to find something to replace it with. And I cannot find any other cross-platform library that is easy to use and is secure out of the box, right? And when I say secure out of the box, rats, you can't read the slide. Anyway, encrypting is one line of code. You call encrypt. Decrypt with a password. Decrypting, one line of code. It's a catch. Try, throw, catch, decrypt, just like you think it should be. And just like all the other ones do it, their back end does it really insecurely. You can't see anything in this slide. What I'm saying here is it's also ported to lots and lots of platforms. So it's on PHP, because you all have PHP in your back end, and it runs on PHP and Python and Go and Ruby and C# and C++ and lots and lots of implementations. Okay. But that's what I recommend. There are lots of reasons you can't use our encryptor. Our encryptor is not magic dust. It is a format. Everybody in your system has to use it because it is a way of encrypting. It's not just AES. It's a way of putting things together. So how should you put things together if you were going to do it yourself? In order to say how, I need to explain what AES is. AES does one thing, well, two things. It can go in one direction or the other direction. It can take 16 bytes of plain text and turn it into 16 bytes of ciphertext. In order to do that, it needs a key that is 3 specific lengths, right? One of 3 specific lengths, and that key needs to be effectively random. That is all it can do, 16 bytes, period. And you go, but I don't know, I use AES all the time, huge megabytes of stuff, and I use my dog's name as the password, and that doesn't seem very random. It's like, yeah, that's true. Because you are using AES, but that's just one piece. You have helpers. There's all these helper pieces that go around to allow you to do that, and the helpers are where things go wrong. So what are the helpers? First, you have to generate a key. You need to figure out how to encrypt more than 16 bytes, and you need to make sure that things aren't changed in transit. So, this is the thing that got me going and writing crypto libraries. I saw this everywhere on the internet, and this is hopelessly broken. What they're doing is they're taking a password that the person typed in and just copying it byte for byte over to a key. Well, that's really bad because, and it truncates it. So if the password is longer than the key length, it just throws away the extras. That should be the first warning flag. It's, wait, I threw away part of the password? That seems wrong. But also, the main problem is that it truncates long passwords. But it only uses this tiny part of the key space because it's only the things people type. Well, AES is key space. AES 256, or especially AES 128, just starting with the small one. AES 128 has a key space so enormous that every single thing you could possibly type, I mean literally everything you could type on a keyboard with an English keyboard, everything would use up 0.00001% of the AES key space. It's tiny. That's why, remember when we talked about things happen millions and billions difference? That's the many orders of magnitude too small. And the AES 256 namespace or key space is so enormous, I couldn't write down the number. The number of zeros got stupid. Okay, so what should you do? You should use PBKDF2. Password-based key derivation function. That's actually what it's for. It's for this. It's also useful for passwords, but it's for this. So as we already used it, we saw it. Remember what we needed for it. We needed a salt. Well, so if you have a format, if you have a way we're doing AES, you should be looking, and you're using a password, you should look around and go, where's my salt? Where's the salt in the format? Because usually for encryption, you go ahead and use random salts. There's no reason to use deterministic salts here. You should use random salts because you stick them right in the format. So that's what you should see. If you don't see something, something's fishy. Okay, second one, initialization vector. I told you it can only handle 16 bytes. Exactly 16 bytes, not even less than 16 bytes, exactly 16 bytes. That's all that works in AES. So, how do I do more than 16 bytes? Well, what's the easiest thing I can do? I'll take the first 16 bytes and encrypt them, second 16 bytes and encrypt them, third 16 bytes and encrypt them. Easy. It has a name, it's called electronic code book. It's a legitimate mode of operation. It's possibly the worst possible mode of operation you can imagine. It barely classifies as encryption in many cases. Let me show you. Picture, right? Bitmap image. I'm encrypting it with electronic code book. Super secret. ECB keeps patterns. The thing is, every white pixel is going to encrypt to the exact same image, to the same color, right? It won't be, you don't know what that color is going to be, but every white pixel will be the same color. Or every block of, it's actually every block of 8 white pixels. But every little block that's the same shows up the same. You need to destroy those patterns in your data. How do we do it? There are lots of answers. There are better answers, but the one you're going to use is called cipher blockchain. Why? Because it's ubiquitous, it's on every platform, it's well understood, it's easy to use correctly. You're just going to use this one. There are other ones, but you're going to use this one. It's called CBC. Now, this is good. This breaks up all that stuff, awesome stuff. You'll see this little thing up here, initialization vector. It's like, what's that? Well, the way that CBC works is it feeds each block of ciphertext into the next encryption. So you're constantly churning all your data with encrypted data. And encrypted data is you can think of encrypted data as being random. So you're basically sticking random noise in each subsequent thing. But what do you do about the first block? Right? You don't have anything before it. You use an initialization vector. It's your block -1. right? The problem is stuff like this. This comes from the header file for Common Encryptor. And people have this all the time. They say stuff like, optional initialization vector. It's not optional. That just means use the initialization vector of 0. There is always an initialization vector. It's part of CBC. You can't avoid it. Well, 0 is always going to be the same, so that's kind of the same as not having one, right? I mean, that gets us back to the problem in the early stuff. So it is not optional. You need it to be different. You need it to be unpredictable. It doesn't technically have to be random, but the easiest way to do it is to make it random. So you just make it random. So you should see somewhere in the format a random initialization vector. Third problem. Now, this one you're going to have to trust me just a slight bit because I used to try to explain this, but it's actually super complicated. You will have to trust me slightly that you can modify things that have been encrypted in ways to cause it to decrypt the way I want it to. So you send a message and it says, send Bob this much money, and then I get it in the middle and I turn it and say, no, send Eve this much money. And then I send it on. And you can do, that is a thing you can actually do without knowing the password. It's a side effect of how encryption actually works. So how do I know? How do I know it hasn't been messed with? In transit, well, remember how we often check things? It's with a hash. And we have a hash. But I can't just use a regular hash, that's no good. I need an encrypted hash. Well, so you could just hash it and encrypt it, but there's a better way. We call it HMAC. This is just the standard way it's done. And in the security world, you just always want to do it the normal way. Don't try to make up your own solution, because they often don't work the way you think they do. And this is very, very well studied. There's an HMAC. So HMACs are encrypted hashes, kind of, and they need a key. Well, so the only thing that you had coming in was the password, so you probably need salt. You may need salts for the HMAC. Again, you should be looking at your format going, where's the HMAC? If there's no HMAC, you should be, again, very suspicious. If the message length, if the entire message is the same length as the stuff you put in and there's no extra stuff, it's probably not a very secure format. So you need an HMAC. Encryption is actually really hard. These are a few things you could do wrong. Just a few of them. These ones I underlined, these are the ones I did wrong just building my own encryption library. And I actually study this stuff a lot, and I made all of these mistakes. Don't build your own AES format. Rob, you built your own. Yes, I know, and I hate it because I can't find one that works. And that's it. You need a key derivation function. Use PPKDF2. You need some proper mode. There are a lot of better modes, but you're probably going to use CVC because it's what everybody has. You need a random initialization vector, and you need authentication, an HMAC. Encrypt, PIN, data protection, salt and stretch your passwords, and use AES securely. Like I say, this will be the, I'll have it up within the hour, so I'll make sure to get the latest, all my latest stuff. There is already something there, but it's missing some of the links, and I'll go, and this is how to reach me. Thank you.